So, hello everybody.
Yes.
Okay.
You're recording, yes?
Yes, I'm recording.
Good.
So we start today Mystery of Physics number 3. And what I will tell in the beginning, the continuation on the relativity principle. There's the main thing, is appeared to be Einstein was thinking that the relativity principle will be the center of all physics, actually. He was trying to find it out for all his life. But other physicists did not support him at all. So nobody was thinking about it for 100 years or something about. But it appears to be that Einstein was right at the end. So the relativity principle, I spoke about this as Galileo Galilei relativity principle, then Einstein relativity principle, which actually was a little more to the absolute, because there was he introduced the speed of light, which is absolute in any reference system, any reference frame. Whatever you do, speed of light is still speed of light. It's still exactly the same. Now we're talking about the generalization of these relativity principles. Next, so the next Einstein introduced a little more generalized relativity principle, which is going from so-called inertial frames. If you remember, was the frame which is moving at the straight line and not accelerated, so just in space, right? Of course, no forces applied, no nothing. That's called inertial frame. So he moved from inertial frame to accelerated frames. And what he noticed that for example, if you're moving like in the elevator, right? But not on Earth, but in space, right? And elevator is accelerated here with acceleration like a. Acceleration is increase of speed per second. So it's measured in meters per second squared. Per second, meters per second. So when you accelerate this way and you are somewhere here in space, of course, your weightlessness, right? But when the elevator starts accelerating this way, you got the weight, which press you to the bottom. That's probably everybody understands, because when it's done exactly opposite, when we have Earth, right, and we are moving slowly down in the elevator, right, and then suddenly the rope broke and you start falling. When you're falling, free fall, acceleration is called g, right? This acceleration of Earth gravity. It is 9.8 meters per second. So you started falling, and in this elevator you will lose any weight. So that's these things he thought about, this simple examples, and what he got out of it, that actually you see the gravity of Earth, it's totally nullified when you are falling freely. When an elevator is falling, or you're falling, or whoever is falling, you are flying with no gravity.
I'm not following, because it's gravity that's making you fall in the first place.
Yes.
You don't feel it.
Yes, you don't feel it.
You're still falling.
Yes.
You're still subject to gravity.
Yes.
So what do you
exactly.
mean?
No, you're right. Don't go too far. You're right. But because you don't feel it, okay? Not only you don't feel it, your clock would not feel it. You can try some weighting machines, they would not feel it. Actually, no device will feel it. And this is an interesting example, right? So somehow no device can measure any gravity when you're free falling. So Einstein noticed this, and he got out of it his principle, which is called general relativity principle. General relativity. There was like initial frames relativity. It was called special relativity principle. This one with inertial frames, right? And general relativity principle was actually suggested by Einstein in accelerated frames. You see, the frames are accelerated by with certain acceleration or free falling, whatever, because it's acceleration too, right? Of the of the gravitational pull.
Question: why did he call it general?
We'll see. We'll see. General because it's generalization. Before was inertial frames, now are accelerated. So it's a generalization, not the full generalization, but step forward, right? So what then he did? Then he did a radical move. He said, okay, because we cannot distinguish while falling, we cannot distinguish the gravitational pull from the acceleration with g, right? So he said it is the same. That was his radical move, and from this, he derived general relativity theory, which is called GTO, like general relativity theory, right?
So can you repeat what is the same?
And
the acceleration and the gravity?
Yeah, acceleration equals gravity.
Makes sense. The gravity is what generates the acceleration.
But only in certain cases. Acceleration is not always the same as gravity, right?
Only if
okay, actually in all cases.
Ah.
So this is general relativity principle.
But
it's exactly the same thing, identical.
But some accelerations aren't the same value as gravity, so they go faster or slower.
Yes, of course, accelerations. There may be accelerations. You may still talk about accelerations. You may still talk about gravity, but they're of the same origin. That is the idea of Einstein, right? And to implement this and to understand what is it, right? So he had to introduce mathematics, which was developed in the middle of 19th century by Riemann. It's a great mathematician, and it's a very complex mathematics. Trust me, it's the mathematics of curved spaces. And because special relativity was already talking about space-time, not only space, right? So it was four-dimensional continuum, right? So here, using this mathematics, he used four-dimensional space-time, but curved space-time. Curved means, like, for example, what is curved space-time means? Like, for example, two-dimensional, 2D curved space is our surface of our Earth. Right? Like we have North Pole here, right? We have equator, right? This is curved because it's not flat, right? So, for example, the analog of the straight lines in the curved spaces are the lines that have the shortest length. They are called geodesics or geodesics. They're like, if you go straight on Earth's surface, you will go by this geodesic line. Actually, it's not a straight line in space if you look, right, because the surface is curved, right? So these geodesics, like, for example, some of them are like equator is a geodesic, the shortest way from here to here, right, from A to B. The meridians, this is meridian, one meridian, right? Or, for example, another meridian, like this, right? If you look here is a straight angle, here is a straight angle too. All meridians, they cross equator with a straight angle. On the surface, of course, measured on the surface. So you will see straight angle, maybe you remember how much is it?
90.
90 degrees, right? Another one plus 90 degrees, right? I want to sum this triangle, right? We have triangle of the shortest line, analogs of straight lines, and here is some angle alpha.
Can I pause for 1 second?
Alpha.
As I'm confused because
Yeah.
there's a very interesting point in geodesics, that geodesics, in that they're not two-dimensional lines, they're three-dimensional lines because of the curvature.
They n-dimensional. It's up to you.
Sure. So why would two-dimensional plane geometry apply?
No, each
It's not a
geodesic.
90-degree angle, actually.
I got it. Each geodesic applies only to certain amount of dimensions. For here, it's 2D, right?
I see.
In 3D, it's another geodesic. Again, in our space, because it's curved, our geodesic are not straight line either.
Correct, yes.
But it's not like this, they're a little different. But anyway, they're not straight, yeah.
They're not. So my question
Right, for
is,
example,
why would the
planets-
angles and the Pythagorean theorem still apply?
No,
Because
no, no,
we're
no,
not
no. I'm not,
reducing straight
I'm not
lines.
implying yet. We're
Ah.
talking about this theorem that in the flat space, you know, sum of the angles in triangle are 180.
Mhm.
Remember, like 180.
I do, yeah.
It's flat.
If it's
in
flat and
flat.
straight lines, yeah.
And here you see it's 90 plus 90. You see triangle, 90 plus 90, already 180.
Yeah.
And plus alpha, which can be anything. Like here, it's alpha even more. If you go like this, you can go the whole circle, still be the triangle formally, right? But the whole circle is 360. So the sum of all angles in that two-dimensional space, it's always more than 180. Always. Sometimes greater more than 180. It's just example that curved space are a little, you know, paradoxal. A lot of interesting things. The other things in curved spaces is that the terms like inside versus outside, they become confused too. Like for example, like again, two-dimensional space but a little more interesting. It's like I don't know how to call this in English. This the donut, but a little deformed donut, right? For example, we have this like surface, right?
Mhm.
And we have here like a handle. So it is sphere and a handle, right?
Okay. Like a purse.
And you understand that in two dimensions, we're not only moving in these two dimensions, we're not going out of the surface, right? But also, if we try to look there, so our vision lights will be too in this surface, our vision light, right?
I'm sorry, our vision.
Vision light, whatever, like if you use the flashlight here, the light will go
Oh,
like
okay,
this.
a line of vision.
Line of vision, yeah, line of vision. I'm sorry, line of vision. So if you take a look at such thing, right, you will see that. For example, we have stars here all over the surface, everywhere, right? For example, and you come close to this funnel. Oh, I will come close to here, right?
Mhm.
And look inside. What you will see? You will see this. For example, you may see stars that is here because the line of sight goes like this. And not only this star, but many other stars which are there. So inside this funnel, you will see the whole universe. Why I'm picturing this? Because you see that outside, this is outside, right? But this is inside. You look inside the funnel and you see inside the whole universe again. It's sort of like you may think about it like optical illusion, but it's not only optical, because not only light goes this way, but any matter goes this way, and you should understand that interaction or force, interaction between material objects or forces between material objects are carried by the material particles actually. So if you put planet here and planet here, they'll be attracted through this line by gravity force. So all the forces go the straight lines, the same lines as light. Just a little paradoxical thing. So inside, so it is true that this planet that you see from here, right, it is really inside there, and all the universe is inside. And inside not only by vision, it's not only optical illusion, it's totally materialistic inside. By any means, any device you use to measure, you will find it out. That's one thing. Now, So this is Einstein and his theory of relativity, curved spaces and everything, right? Now, to get more unification of the theories that we talk, remember that quantum theory and general relativity was not unified, was never unified for 100 years, right? So what is this? Was introduced the principle of absolute relativity. Or if I call it his relativity absolute, because actually again it's not that about relativity but more about absolute, but absolute is relative, so it's a paradox, of course, right? Okay, so how we come to this principle, right? This principle of absolute relativity. So it's the total generalization of relativity principles, all of them. Imagine we have something like our universe, whatever it is, some, like in the beginning of Big Bang or whatever. Nothing else, only our universe exists. We don't know what is this. And we have frame of reference. We have frame of reference. Frame of reference actually, this frame of reference is in the beginning, it coincides totally, so it's identical to the whole universe. So universe is equal to frame of reference. Or we may say that universe looking at itself. Like for example,
From the inside.
it may be like this, right? So why not, right? We can look at ourselves. What's the problem? And then we do this. We make some mental experiment, right? So we start. How physicists usually say, we turn on time. Turn on the time. Switch the time. So now the time was not moving, now we turn on the time. What it means? The changes, we allow changes to apply, right? So the universe starts changing. It starts changing. But the universe is changing, but the thing that we call frame of reference, our frame of reference, we don't change it. So we allow changes only to universe. So the part of it, right, will still be our frame of reference, but the other part continue changing, and now universe is something like this, right? It's changed. What we'll see in our frame of reference, so what our device, what is frame of reference? Now it's materialistic frame of reference. It's devices, clocks, all kind of experiments, our eyes, everything, what we have around us, which we control. The main thing, we control it, so it's a controllable situation on this part, but on another part it's not. So the universe changed, and we call this time. Like time is running, all around is changing. We see the change, so we call this time. The changes means time, right? Okay, this happens when only the part of the universe is our reference frame. But imagine that we still have the whole thing, our frame of reference, and we change everything together. So universe is changing, and our frame of reference changes with it. In the same way, it just never goes out of anywhere, never separates, never distinguishes from the universe. In all parts, in everything part, and blah blah blah, whatever, we coincide as total absolute identity, right? So we are not differ in any way from the universe. So what will happen in this way? What do you think? The universe changes, right? And we change with the universe. So it's very similar to the way that something moves with the speed of v, and we moves with the speed of v. What changes? Nothing. We accelerate, and the frame of reference accelerates with the same level. Again, nothing changes, right? This is general relativity. Another thing, like the size. Size was like this, size become like this. But we expanded the size exactly like the universe, right? So what will the universe be looks like for us. Nothing changes again. The same thing, if you think about it, there's some sense in it, right? So you may apply changes of your frame of reference in the way how the universe changes, and then you will see nothing. It means that in this case, when the frame of reference is changing together with the universe itself, it means that time is not running. So you may say that proper time or time in the rest frame. You see, this frame is like resting in relative to the universe. Resting, it's not changing. So you may say that the time or tau, usually this corresponds to this rest time, or they call it proper time. I forgot last time. His name is proper. They call it proper time. This proper time in this case, actually, according to this new principle, it's always zero when the frame coincides totally with the universe. Yes?
How do you know anything's changed then?
Nothing. You don't know. In this case,
Then for all intents and
nothing
purposes,
changed.
nothing has changed.
In this is just thought experiment, right? So in this case, nothing really changes. You cannot know anything.
You see that
Universe changed, but you changed with it, and nothing happens to you.
But
It's
as
called
a thought
observation.
experiment,
Observation.
If you can't observe the change in any way, there was no change.
Yes, it's in certain way you may say that. Yes. So it depends upon how you put it, right? Yeah. I agree. So the change are relative. If you put it another way, all the changes are only relative. There's no change with no relation with anything. Like for example, information. Information, term information, right? When you can get any information from something, but something changed. If it's not changed, no information. So even the definition of knowledge, of information, it's connected with the changes. No changes, no information. Same things here. So this absolute principle.
But the thing you're getting information about doesn't have to change. Something outside of it can change.
Side again, if you have on side, there's something's changed. If nothing changed, we're talking about the whole universe, remember? Okay. So now we return to this part change, right? Universe changed that's another case already, right? Universe changed, but your frame of reference did not change. What will happen? Time pass, right? You see universe changing, right? But you, in your frame, you may say your own time or whatever, you don't change. But the interesting thing is, you should notice that exactly like in the previous case, you cannot actually observe your own changes, because in this case you coincide with your own part of universe. The only thing that you can observe only changes outside your own frame. This is the result of this absolute principle. If you put actually the formulation of principle of absolute relativity, it means that if your frame coincides with the universe, right, so there are no changes at all. This is like one of the formulations of the principle. So if it doesn't coincide, then you see the changes, but these changes are only relative, and they relate to the universe outside you, outside your frame of reference. So you see some changes, and you may consider this that time is running. T does not equal 0, right? And now we make a certain trick. Again, it's a thought experiment. Certain trick. You start changing. Now you start changing by yourself because you control frame of reference, right? You start changing your frame of reference in the way exactly how it will be changing with the whole universe with your total frame of reference was moving in the previous example. Like exactly. Like we said it, we saw it in the a recorded in the movie or whatever, right? What will happen with your observations in this way? You may notice that when this frame of reference coincides totally with this last thing, right? This is not distinguished from this because nothing changed. Remember in that moment. But in the process of moving, you will see that the whole universe will start changing from this state we already had it, right? Because it's changed already to that moment. It is changed, remember? So when we start moving frame of reference or changing, it looks like t goes opposite, goes this way. Time goes back. It's exactly like we turned back the recording. So we recorded it this way.
Didn't we start from A and go towards B, which would be moving forward?
You see, I will say, you see, this like you have films, right? A film, right? With this, with the pictures, right?
Right.
Changes this way, right?
But for you, there was no change. Remember, from your frame of
No,
reference.
when your
But
frame
he's
of
saying you pretend almost like you.
Yeah, so you pretend it's changing. So for you, you start moving the film from A to B.
yeah,
So not backwards, forwards.
No, but the universe is what looks like it's going backward, not you.
yeah, universe, of course. For you, still nothing. Your changes you
Why would
cannot.
it be going backwards if you didn't ever see it go forward?
No, you see
You
it go
see it
forward.
go
I told you. Look at this. Look at this.
When?
Here.
Because you just got a device.
Ilyush, look here. Look here. You're not looking. Look here.
Yes, I've been looking.
Yes, this part, the part of the universe starts changing. You see these changes. The time is running. You see the changes. You see it here, and you may even record them. Then like the changes in the universe, like you stop changes in the universe and you start changing in this only in your frame. Universe is still there. You not change it at this moment, but you start changing your frame. So the changes that you see right now, observing change, they will go backwards. Like you go this way on this record films. It's the same thing as like something passing this way. It means that you may go this way, opposite, and still it will be like it's the same thing. You have frame of reference, right? If something is moving with a speed v, right? It's the same like your speed, your frame of reference speeding here, and this is have 0. It's the same thing. You see, this and this moving in relation to this, but you can do this and this moving in relation to this. Then depends what you do, and they move opposite all the time. So if you move this going relatively to this, it's going opposite. This is again, it's in the principle of relativity. The same thing with acceleration and whatever. Okay, for example, you may increase the size of the universe, right? But you do not increase yourself. You will see that your universe is expanding, right?
Sure.
Agree?
Yeah.
Agree. Now you expand yourself, but the universe stays the same. What you will see?
You're asking?
You catching up
Yeah, I'm
to
asking.
the universe.
Universe will be smaller and smaller, right?
Yeah.
So this is exactly that. That's all. The same thing I shown here in the more abstract, more abstract things.
I understand what you're describing. My only question is, how do you prevent the universe from continuously, how?
No, I'm not preventing anything. This is just thought experiment.
I got you.
Thought
Because
experiment.
that's the only
And this
part.
is the end of this thought experiment is that actually when we move, when the universe is changing, right? And we cannot observe the change. Remember, when it's changing together with this frame of reference, right? There is no change, but this may be divided into 2 points. The first, only universe changing, then the second, only frame of reference is changing. The result is still the same, but our observable picture will be totally different. In this case, nothing happens at all, right? In this case, we have first t more than 0, some t passed, and on the second, when the frame of reference is going back, t minus 0. T1 and T2, and of course T1 plus T2 totally 0 because no change at the end. See, right? So So this T2 minus 0 actually, it appears to be this anti-time that happens to be each time when something is changing with us, right? This anti-time, it behaves totally like a space. If we have time and we have anti-time is space. I would not go further, you may think about it, but by introducing this thought experiment with this absolute relativity, we actually introduce space-time as one. As one. Where space is anti-time, it goes back in time. And it's easy to see that everything that we see around in space, actually it's in our past. It's our memory. If you look around, even the head, right, that we see, your hand, it's in the past. Nothing you see even in the current time, nothing even in the present. Everything is in the past. And the future you cannot see. So all you see the past. So it means that you see the memories. And memories, sorry to say, they are back in time. Memories are back in time. So you may think this way or that way, but space is actually, and physically, I've shown it mathematically, it behaves exactly like anti-time. So that thing. So what means this anti-time? So we have t minus and t plus, right? What is this? Because time is not changing, it is called time loop. And remember we were talking about time loops before, electrons that go in loops, right? Back and forth and blah blah blah. So this picture exactly goes, maybe simply derived from this principle of absolute relativity. It goes to the time loops everywhere. Everywhere. And now what we see now in this picture, we see in this case, like with this principle, right? We see that the universe appears to be like a whole, like I say, ball of time loops. Like lots of these threads going like this. How many of them I will tell you, right? The number of these loops is about number of the particles, like protons, neutrons, or whatever in our universe. It's 10 to the power of 80. So 10 and 80 zeros after this. That amount of loops. What's the size of this thing? Size is, I wouldn't say right now, but it's similar to the size of elementary particles. So universe has the size of elementary particle. Each quantum or elementary particles, it's equal universe. Because each loop actually is a quantum. The loop is a quantum. And many of these loops create our universe, which exactly are just the same loop, just taken many, many times, 10 to the power of 80 times. And it's the same loop. All loops, all time loops, are identical. Or, in other words, is undistinguishable, right? You cannot distinguish one from another.
And why do they look like they're behaving differently? If all the loops are the same, it would just look like a circle.
They behave, yes, there are some differences. Remember, there's energy difference, right? And energy, actually, it's if you take one particular loop, right, it has more or less amount of loops before it in time. Because its loops are rotating, right? So the more rotations you have, the more loops you have, right? Not loops, the length of amount of loops, right? Before you, it's still the same loops, but before you have different times. And now, how many actually? What the speed of this rotation? The speed, it's very easy to calculate from these main equations. Remember, this energy is H omega, H is Planck's constant, or energy is mc squared, right? So because they're equal, right, you may see that this omega, this is frequency of how many per second these things are doing. Our universe, actually, it's the whole thing, because the universe is equal to quantum, each quantum. So omega is mc squared divided by h. And this is, you can easily calculate, like if you substitute here like the mass of proton, it will be like 10 to the power 24 rounds per second. 10 and 24 zeros per second this thing is rotating. So, and remember that small, if you look into small, it can be big. The space, remember? I spoke about this, right? So this looks small, but at the same time is big, because when we're trying to measure along these lines, we get the intervals and we get the distances that we see in our universe. So these light years and light years and light years, but they are all consisted of these rotations with this Planck formula of each particle, each quantum is that. So just for you to understand how it looks like the universe in this thing, right? It is identical to the quanta, at the same time is big, right? So they're rotating with the speed of light, but from the frame reference of the quantum itself, nothing changes. The time stands. Remember when you have the frame which coincides totally with the universe, nothing changes. That's why we have this Lorentz formula. Remember that we talk about time, right? This the rest time or proper time. It is t.
Yeah.
This. That's why this formula goes out. Actually, mathematically, it's not that easy, but pretty simple to derive all these things from just one principle. So just one principle derives everything. And of course, it derives that the particles are identical, and also all these quantum phenomena. That's a particle. The quanta can be anywhere in the universe. Of course, it's anywhere in the universe. It's the universe itself. It's anywhere in the universe. Yeah. Okay. So this is.
So is.
Yeah.
Einstein came up with general relativity.
Yeah.
Is absolute relativity?
This is mine.
This is yours.
Yeah.
Okay.
Yeah. This is actually the last step, because there is no. You cannot go any further. This is absolute relativity, or here's a relativity absolute, which is this. Mm-hmm. Not exactly that, by the way. It's a little more with this, but this is not physics. If you go further, you will come to which I called theory of subject. This is further generalization, which includes not only material things, but also consciousness and everything. But this is another thing. Now, what I want shortly to talk, I think we have enough time still, just to finish this, that for you to give you some example how this theory can go to technology. So to some really things that you can really touch. These things are, you can make experiments on that. Of course, thousands of experiments are made. It's all, the theory is very, very good correlation with the experiments. But interesting enough that very interesting thing can happen when you really apply these things to technology. And to do this, I will remind you one thing first. Remember when I talk about Bose-Einstein condensate, right? I told that even when it passed through the barriers, like, for example, superfluid helium, right, goes like over the wall, for example.
Yeah.
Right. It preserves their vortices, swirls that they have. Remember these things. Mm-hmm. So all superfluid goes somewhere, or through thin tubes or whatever. Even actually it can penetrate even right through the barrier, right through the wall, because helium is pretty penetratable, and superfluid helium is very penetratable. So it can go right between the atoms. Even if it goes between the atoms, still here it will have the same vortices as here. So it carries it with them. Now, there were lots of effort made to create not only liquid helium, superfluid helium, but solid superfluid helium, like crystal, like crystal helium-4. Experimenters, they are pretty close to this, and it was demonstrated that that something like this exists. So experiments were already done. It's not like only theory. But what will happen in this case when we have like superfluid crystal helium? It will be able, like a liquid crystal, like a liquid helium, penetrates through the walls. So it will go through the wall. And it's not like very difficult to him to go through the wall. It's not like that it will wait like for hundreds of years. No, it will pretty fast can go through the wall. It depends upon the experiment, but it can, right? And interesting enough that when it go through the wall, it preserves everything that it has before. It preserves its form, it preserves its crystallic structure, crystal planes, even defects. If there are defects here, some maybe cracks or whatever, right? They will still be here. Actually, you may think about that if you add here like a head and legs and whatever, they will have them here. And not only that, if something is changing there, like a clock or whatever, it's made of this, the clock will still be here. So this is still a little fantastic, but it's coming to it, because all the laws, they say that should be like this. And experiments already come to the crystal, to the superfluid crystals. They come to here. And just remind, something interesting is coming, right? Now with this thing. Now we'll talk about space and time machines. How they work. All these things, they allow you to create space machines, starships that can reach any star, anywhere, any galaxy, and time machines, which can allow you to reach any time, past or future. How they can do it? To this, I need to remind you, if you remember, or if you not, maybe just find out now, how optical lenses work. Do you know a little about it? How optical lenses work?
Let's assume we don't.
Yes, that's what I'm assuming.
I don't actually know.
For example, if we have a lens, right? Usually they call it thin lens. Thin lens. We have so-called the line which goes through the center of the lens, which is called optical axis. Right through the center of the lens. It's lens like this.
Okay.
You understand, right?
Yeah.
And we have, probably you know that there are 2 points on this lens which are called focus points.
Yeah.
It's 1 and 2, right?
Yeah.
Well, and how you actually create the image that this lens creates somewhere. It's pretty easy way. For example, you have like a man here, right?
Yeah.
This is his head, this is his legs, like simple, right? Like this, right? So what you do to create his image here, to understand how lens works, there are simple things that if the light, so photons, right?
Mm-hmm.
Photons are pH. Photon.
I think
pH, I think, yes, that's photon. So photons go like this, parallel to the axis, right? So the general law is that the lens make it go through the focus, like this. This is general law, right? The other two general laws for the lens is that if you go through the center of the lens, right, it go just straight.
Okay.
That's one thing. Another thing which I will use here, it's just opposite to this, because you can go with like this or this way. If you go through the focus, it will be parallel the axis after the lens. So we go like this, right? Is focus. Here it is parallel.
Okay.
And here will be the head of the image. And this point goes straight through this through the axis, because it goes through the center of the lens, remember? And so here we had this point. And this point again, we can do it like this, but anyway, it's easy to understand it. It goes like this. So this will be the image.
Okay.
So now the interesting point is that usually people talk about the images, like optical images, like they're not materialistic. But they are actually real matter. Because what is here around when you're standing here, you're standing under the light, like sun, right? Under the rays of sun or any lamp.
Okay.
So these rays comes here, they are photons too. Photons are reflected by you and go through the lens. Photons are real particles. They are real. Quantum particles, but real material particles. So these lines are the lines of the real material particles. So here around you, you have sort of a cloud of photons. Of course, they are scattered. The term is scattered by you. Okay? They're coming from the sun, reflected by all your parts, and they're somewhere around you. And then these photons, they go through the lens and create here your image. What is this image? Actually, it is a sort of a cloud of these photons, yeah?
They got
Exactly like this. And this image is materialistic. It's not like any, it's a real thing. You can measure them, you can record photons, you can put whatever. You can put eye here, of course, but eye is not only simply measuring, it's getting photons, right? Getting the energy and produce electrochemical pulses in your brain. So why I'm talking about this that long? Because I want to say that lenses are a very interesting thing. They actually create the material image of one thing in another place. In this space time, in this space point, into another space point. And of course, it takes some time, right? But time, and it passes some distance, right? But for the photon itself, remember, because it's going with the speed of light, v equals c, this rest time or proper time of photon is equal to 0. So photon doesn't even notice that it comes here. For photon, this point, like A and point B, are equals the same, E equals B. In his frame of reference, or its, whatever, this is one head, it's not two heads, it's one head. Because there is no distance between them. This is distance in 4D distance. This is distance in 4D dimension, 4D space-time, right? So there is no distance between these points for photon. It's for us, it's our frame of reference. Yes, this is relative, this is paradox, of course, there are many paradoxes, but it's like, the niche is like this. What it means, that 0 thing? That actually, if you're here, you got exactly the feeling, everything of photon here. And at the same time, for the photon, time is tau is 0. So if something is changed here, it's exactly immediately changes here for the photon, because it's the same point. You cannot change this and without changing this. And by the way, it's difficult, but if you can change this, you will change this, and this going back in time, right? If you change it back like this. But for now, it's okay to say that it's the same for The same for going from the past, right? So now, so this is how lens works. Now we have lenses in the space outside, like they call gravity lenses, like a star and some distant star, like a planet, for example, right? Mm-hmm. The rays goes here, photon go, but photon is material thing. The gravity pull of the star makes it like this, okay? And if another photon goes like this, the gravity pulls like this, like here and here, point close to focus or whatever appears. So, so some star, any star or black hole or whatever, or maybe planet, they can work like so-called gravity lens or gravitational lens. And what we'll see here, for the light, again the same thing, right? There's if something is here, right? So you see the image here and everything. But the interesting point that this point and this point for photons are the same. And that's okay for the photons and for the optics of photons and everything, right? But exactly the same thing happens with all other material particles. Exactly like these material particles go through the handle, and remember in this picture that of the universe, right? Exactly the same thing happens with other particles. So for example, again, imagine planet here, and we have some whatever telescope here. Now I'm talking about telescope, but telescope which I call maybe material telescope. That actually contains not only optical lenses, but all kind of lenses, like the gravity lens that with the star. Remember this? Right, it's exactly that type of material telescope because it curves not only lights but any rays of any kind of matter, whatever protons, neutrons, whatever particles we have about a few hundred different particles. All of them are curved, and they will create here a materialistic image which contains not only photons but also protons, electrons, neutrons, everything. It may be weak. It's not dense, right? But it's exactly the image of what we have here. If you have here a man, here will be image of a man, just not dense, like a ghost, but exactly of these particles, the same consistency. And interesting enough, because for these particles, actually their own proper time still zero. Remember that particles, not photons but other particles, they move like this, zigzags, but they're all zigzags is speed of light. So we see that they are not, looks like they're not moving very fast, because they're doing it like with the speed 10 to 20 by to power of 24 things, right? So this like vibration. So it looks like it stands in maybe rest in time, but actually it's going with the speed of light. So this the proper time for them still zero, for this here too. So these protons, blah blah blah, neutrons and everything are exactly the same which we have here. They are not only, and they are not delayed by time. Time is zero. They're not delayed by space. Space is zero too, according to the space-time theory of relativity. For the protons or whatever, who they're moving with the speed of light, this space just jammed into zero too. So those points and those points are exactly the same. It's like your universe is glued with these points too.
But only from their point of view.
Yes, but it's enough, trust me. The point of view, this thing tau, right? Tau. It is a so-called invariant. It's exactly the same in any frame of reference, the tau. Not the time, but tau. It means that it has significant physical thing under it. So it's not changes. So yes, frame of reference, yes, but what will happen? What will happen in this case, for example, if you create such material telescope, right? Because here you have image of the part of some maybe planet here, right? if you touch it, you touch this part. You may make analysis, physical analysis here, like we do spectrums right now in optical spectrum. Here we can do whatever measurements here, like a real, like you can touch, you can weigh this thing, you can do many things. It still be physical and it'll be exactly like this, but this time is much than your time, this present time, much smaller. This was in the past, right? So you go from here to here in the past. This image is image of the past, which happened many years ago, like thousands of years ago. So this material telescope will be actually a time machine, really, because you not only can measure something, but you simply can go into this. It is exactly your entrance into the past of this planet. So this is real time machine. By any means. And this can be, I probably won't talk more, but it can be done with this BEC superfluid solids, like helium-4, because it does exactly that. It can be this thing can be used to create this kind of telescope. So it's doable, not today, but in the pretty close future. Not like somewhere in thousands of years ahead, but somewhere in some dozens of years, a couple of dozens, 3 dozens, something like this. So it is doable, at least for experimenting in the beginning. So this way we're talking about this time machine, right? The same thing can be done to the future. What do we do? There is a thing which is called projector, like in the cinema.
Mm-hmm.
What does do projector? Projector is totally opposite system, exactly the same but opposite. Dialectics, yes. To the telescope. So it's a telescope backwards. So you have here some small thing, right, which with the lens project you to the big screen or whatever. It's project. And of course, because there are photons traveling, right, there is some time until they come there to the screen, right? Mm-hmm. Or maybe no screen at all. It's maybe in open space still. The image will be here, and this image is materialistic image. Materialistic image. So what is this? This projector, if it's made with this BSC, solids and everything, I would not go into details, but trust me, it can be done. It actually projects any objects from here to the future and to the big distance. Because through telescope we can see like quasars like billions of light years ago and away from us, right? The same thing we can project in the future, and we can have light of years in the future and light of light years, right, in the distance. So this projector is a type of the starship. And trust me, you can do it not only for something like you put here like projector, right? You go into it and you just project it into future and space, right? Somewhere many light years from here. But it can be done, the thing that projects itself to that distance. It can be done too. Okay. Because quantum mechanics is a little interesting thing. It can do the same thing with itself. So it can be projected or projects itself. It can be a time machine that actually can go to the past time. Mm-hmm. Okay, I'm finished. Questions?
Okay. The time machine made more sense to me than the projector, I have to admit.
Or the opposite. Exactly.
I understand that, but I never understood that it's projecting to the future. It feels like it's projecting to the present to me.
No. It takes time, right? That's why it's future. Okay. It will go. It's like imagine there are photons traveling, right?
Yeah.
Or whatever particles. For material projected, it's any particles traveling, right? So particles traveling. It will take some time. So you started now,
yeah,
but it will finish long ahead. So this your image will be traveling in space-time for many years, maybe for thousands of years, right? In our frame of reference. In your frame of reference, because you're traveling with the speed of light, they will be totally zero. So
you'll be young. From
you'll be like yes, of course. You can, if you go back, you can return to the very future of our planet, right? Yes. Okay. Okay. The questions, Ilyusha?
None.
Okay. You understand everything. Okay, guys. Maybe at some time long ago, not now, that's for sure, that we may talk on this stereo subject. But for now, I think that's enough for you to think about it, to understand something. If we're talking about something, at least you have something in your brain that responds to something, right? And I hope maybe you sometimes will think about it a little.
Well, we're always thinking about time machine.
Right.
I mean, exactly. No, I'm always wondering if it's something that can be done.
Yes, it can.
In our generation.
Yes, it can. Now it can. Yes. In our generation, can be done. It depends, of course. If we want to do it right now, it will be lots of investments to be done, right? So, like for example, to make this type of thing, actually what we need, I told it many times to Ilyush, we need this neutronium matter or nutrid.
We don't have access to that, do we?
Access? No, we don't have it on Earth. Yet.
Yet.
But people are working on it really, and they are working with neutrons, and neutrons are close to the maybe already there, but probably we don't know because it's maybe secret thing, because it's a very powerful thing to do. Mm-hmm. So this Bose-Einstein condensate of neutrons, this is exactly this neutronium matter or nutrid that is needed to create these things too. It has lots of fantastic features. It can withstand thermonuclear explosion, that not penetrable by radiation. It's fantastic material. But among other things, it is the material to create starships and time machines. And we're coming to it. We are pretty close to it. Okay, guys. Thank you.
Thank you, Dad.